Hello, it's Scott Manley here. Now, if you're a regular space watcher, you'll know that the Atlas V has a naming scheme where it uses a 3-digit code to define the configuration of the rocket. The first digit is either 4 or 5, that tells you whether it's a 4 or 5 meter fairing. The second digit is 0 through to 5, which is the number of solid rocket boosters. And the third digit is the number of engines on the upper stage, and this has always been a 1. But in the near future, we're going to see something with 2 RL-10 engines on that Centaur upper stage. To be clear, from the Centaur's earliest launches in the 60s, it had 2 engines, but the arrival of the Atlas III, they began to offer a single engine variant. And the last payload to fly on a dual-engine Centaur was actually on an Atlas II in 2004. But now there are a couple of payloads which will be using the capabilities of the dual-engine Centaur. In the distant future, there is going to be the Dream Chaser cargo, and that is actually going to go on an Atlas 552. That is the biggest Atlas V they offer. But hopefully launching early next year will be the Boeing Starliner crew transport vehicle, and this breaks the Atlas naming scheme because it doesn't have a fairing. So the Atlas designation is going to be an Atlas V N22, N for no fairing. Now, some of you might wonder why these payloads are switching back to the dual engine design, and some of you have already come to the conclusion that it's likely because these are heavy payloads that require more rocket to get them into space. Indeed, if you use a launch performance calculator and you put in an Atlas V with 2 solid rocket boosters, then you find that the single engine version can put 13 tons into orbit, and the 2 engine version will be able to put 15 tons into orbit. But if instead you put in an Atlas with 4 solid rocket boosters and a single upper stage engine, it can also put 15 tons into orbit. And that configuration is significantly cheaper. It's a lot cheaper to strap an extra couple of solid rocket boosters on than to duplicate the RL-10 engine, which is one of the most expensive parts of the rocket. In fact, if you think about it, adding an extra engine to that upper stage without adding any more fuel actually means that it gets less delta V on paper. Single-engine Centaurs are actually more efficient when you're pushing payloads onto interplanetary trajectories because there's less vehicle mass. No, the 2-engine decision is all about crew safety. Obviously, adding an extra engine does give them a few abort scenarios where one of the engine fails partway through the burn and then they just burn the second engine for longer. But the other side is that it makes it easier to eliminate the dreaded black zones. Black zones are points in the vehicle's launch timeline where an abort or a failure could lead to the loss of the crew and or the vehicle. For example, the Space Shuttle's launch timeline had all sorts of places where if a solid rocket booster failed, there was no way for the crew to recover safely. The Starliner is going to have a proper launch escape system that will be able to remove the crew and the capsule from the rocket and return them to Earth if there is a failure at any point in the launch timeline. Back in 2005, when NASA was trying to figure out what to replace the Space Shuttle with, there was one famous or infamous study which claimed that human rating the Atlas would be hard because in its the current form, it would result in abort scenarios where the re-entry of the capsule would be so hard and so fast that it would kill the crew. And to be fair, a big part of this argument was driven by the faction that wanted to have another rocket based off of shuttle hardware. The argument basically went that the Centaur was a very efficient upper stage, but it was a low thrust upper stage. So after getting dropped off in a ballistic trajectory, it would take a pretty long time to actually accelerate up to orbital speeds. Which meant that to give it the time that it needed, the rocket had to launch onto a much higher and steeper trajectory than a higher thrust upper stage would need. For example, one study that looked at this on an Atlas 401 found that the capsule would get as high as 270 kilometers before it got into its much lower orbit. So in the worst case scenario, it would basically be falling from that altitude very steeply into the atmosphere. The same analysis on a 402 with 2 upper stage engines would only get as high as 150 kilometers, because it would need less time to accelerate into orbit. But this same study then went on to reconfigure the launch profile for the single-engine upper stage and actually came up with a reconfigured trajectory which would safely get the crew into space and not have any abort scenarios where they would be crushed by the G-forces on re-entry. So NASA's study certainly didn't convince the engineers that were working on the rocket itself, but it was enough to convince NASA, who went on to promote the Ares 1 as their crew launch vehicle. Unfortunately, a 2009 Air Force study concluded that the vehicle wasn't quite as safe as NASA had suggested. In the event of a catastrophic booster failure about 30 to 60 seconds into the flight, the launch escape system would indeed carry the spacecraft safely away, allowing its parachutes to deploy. Unfortunately, the spacecraft would then descend through a cloud of burning debris, which would not do great things to the nylon parachutes. And now, 10 years on, we're going to see commercial crews flying on those vehicles that NASA had dismissed back in 2005. Of course, I should mention that the Falcon 9 flies with a Merlin engine upper stage which has much more thrust than the RL-10, so it can fly a much safer and more shallow trajectory. Also, the RL-10 is one of those engines you can't really scale it up and make bigger because it's an expander cycle engine, so you can only add more engines to get more thrust. In fact, for the SLS, they're going to be using 4 of these on the upper stage. And actually, I think one of the best examples of the Centaur upper stage desperately trying to put something into orbit with not enough thrust is the Cygnus OA6 launch, where they were launching a Cygnus spacecraft to the ISS, and the main booster cut about 5 seconds early. So the upper stage then had to make up 5 seconds of maximum thrust, and it had to immediately start correcting for the fact that it was going to fall back to Earth. So it takes on this very high attitude angle to make sure that it is thrusting away from the Earth. And it ended up wasting a lot of its delta V just trying to compensate for this. It did actually get the payload into orbit, but during the deorbit burn for the Centaur after it had deployed the payload, it actually ran out of fuel. So it was seconds away from failing to get that payload into orbit. Atlas came within seconds of having an unfortunate failure on its launch record. Anyway, I'm looking forward to seeing the classic dual-engine Centaur back in action. Until then, I'm Scott Manley. Fly safe.